Check if a binary tree is balanced. A balanced binary tree is one in which the depth of every node's left and right subtree differ by at most 1. So in this question, the most intuitive way to solve this problem is to compare the height of each subtree and to check if the height is meet our balanced tree condition. We choose to use a recursion method to do it. And in the recursion process, the function will return -1 whenever it fails to meet our recursion. And so more detail will be here. So we have a main function called boolean is balanced, which takes one argument, which is tree node root. So the root node is one and only parameters we have to pass in. And we have to check the corner case. The corner case is when the root node equals to null, we directly return true. Means we don't have to compare the root node to anything. And then we have to get the height of our binary tree. So in order to get the height, we created a function called getHeight. So this function is a helper function to help us to decide what is the height of our binary tree. And since this is a recursion function, we have a base case, which is root equals to null. And then the recursion rule is to check left height and right height separately. When the recursion function hit our base case, it will start to return. And when it starts to return, it will check the two conditions in below. So the first condition is to check if at current level the left height and right height difference is greater than 1. If it is greater than 1, which we know it fails to meet our balanced tree condition, so we defined it as return -1. And we will use this -1 or refer this -1 in our main function here. And then the second condition we have to check is to check if either of our left tree or right tree has ever meet or return to -1. If at some point our left binary tree or right subtree returns to -1, we have to return -1. Means this fails to meet our condition either. Otherwise, we return the height of the binary tree itself. So after getting the height or 0 or -1 in our getHeight function, we could check if the height is equals to -1. So if the height is equal to -1 as we defined in our getHeight function, we know that the binary tree is not meeting our balanced condition, so we return false. Otherwise, no matter the getHeight returns 0 or the actual height of the balanced binary tree, we return true, which means the tree is indeed balanced. So in this problem, the time complexity will be n times log n because we consider time complexity in the worst case. In the situation, the tree will be balanced. And in a balanced binary tree, our recursion tree, the first level of our recursion tree has one node, but the node has one time, has on time complexity. Since it's a root node, it takes on time to get the height of the root of the tree. In the second level, we have two nodes, and for each nodes we have n divided by 2 time to get the height. So the second level takes us 2 times n divided by 2 time to do the recursion. And same logic goes to the next levels. And we also have to calculate the levels of our recursion tree. So since our recursion tree is balanced, our level should be log n. For each level, we calculated n as its time complexity, so the total time complexity will be n times log n.